So first, let's remind ourselves what is Analyzer. STK's Analyzer is a trade study tool directly integrated in STK. You just need a 64-bit version of Java installed on your computer and then install STK Analyzer to be ready to use it. The main advantage of Analyzer is being able to perform quickly and seamlessly what-if analysis within STK, collect data from scenarios, and optimize scenarios. Typical examples of the uses of Analyzer in STK include positioning satellites to obtain optimal coverage, predict ranges for fuel requirements due to variations in satellite launch positioning, configuring transmitters and receivers to maximize communication bandwidth. And in our case, we're going to use STK Analyzer with Astrogator in the case of a launch, specifically a case of a launch to GEO. So we have several maneuvers here, and we're going to study how to use access duration constraints in Analyzer to complete our Astrogator sequence and optimize our trajectory. You can take a look at our scenario and you will recognize a familiar name here. So I wanted to recreate an historical mission, which was the flight number 3 of Starship that took place last week. And I wanted to recreate it because there's interesting constraints to put in place. The main constraint being the launch angle, which must take place between the southern tip of Florida and northern tip of Cuba, and fly carefully in between the Bahamas Islands. So we need to reduce the access duration to this airspace to the minimum, to 0. And while doing so, it will be nice to be able to actually analyze which trajectory plan will be the best to optimize our next maneuvers, which are essentially GTO maneuver and change of plane maneuver in order to get to an equatorial plane. So this part of the scenario is fictional here, but we can imagine that Starship will be able to put objects into GEO orbit in our case, and we're imagining here that Starship accomplishes this mission and does not fall back into the Indian Ocean. The objects that I first inserted the area targets object. So I went to insert, new, I selected area target, and I selected the method select countries and US states. So this gave me the option to select several countries with control. I could select a few of them if I wanted, and then I inserted them. And once I inserted these area targets, I wanted to not have just a line of sight constraint with them, but I wanted to have an elevation constraint. And in order to do that, I went to the area target object, and I went to its properties and to the basic page, and I enabled minimum elevation here and set the value to 90 degrees. So that means that it's basically an airspace now, in the sense that my satellite here won't have to have an access with this object just with a line of sight, but it will have to be over this object, over any points of this object. So that creates this kind of airspace object. And then I have my satellite, my Astrogator satellite, where I first inserted the launch sequence here with the latitude and longitude of my launch site. And in the burnout, I have an azimuth of 85 degrees in this case, and a downrange distance of 5,000 kilometers. It doesn't really matter for now because we don't know which is the best azimuth and downrange distance for our scenario, and we're going to find out thanks to Analyzer. A few things about the other segments in my Astrogator sequences. So I have a propagate to descending node segment. I deleted the initial duration stopping condition, that's the default, and replaced it by a descending node condition. So that means that my next maneuver will take place at descending node. I have a target sequence here which the goal is to raise my apogee to geo. So I have a maneuver nested into it that's a long velocity vector, and I made sure to check the check mark here for the delta V magnitude. And in the results, I have a radius of apoapsis selected, which is in the Keplerian elements folder, and I have a delta V. This is for analyzer, and this is in the maneuver folder here. And this will be useful to know the output of my delta V after my maneuver. In my target sequence, I have a differential corrector, which selects the long velocity vector and as a control parameter. And the equality constraints, I have selected the radius of apoapsis equal to 42,160 kilometers, which is geo orbit. Finally, I'm propagating to the apoapsis of this new orbit. And when I reach it, I have a second combined change maneuver, which is basically a maneuver that's combining a plane change and a circularization of my orbit. So I made sure to select the attitude control to thrust vector here with the X and Y thrust vector selected as control parameters. And in the results tab here, I have the inclination and eccentricity, so I can select them and put the goal to 0 in my target sequence. And I have also the delta V, that's for the output of my analyzer. And if I check the differential corrector, I have selected both X and Y thrust vectors here, and my eccentricity goal is 0 to circularize, and my inclination goal is 0 to be able to reach the equatorial plane. So now that I've set up my Astrogator sequences and I have set up in the results of my maneuvers my delta V to be an output that I can use, as well as the access between Starship and the area target that I configured have been computed, I can go to my object browser here, right-click on Starship, go to a satellite plugin, go to STK Analyzer, and here I can see my main window for STK Analyzer, which allows me to configure my variables, my inputs and my outputs. I have various STK variables on my left panel here, so I have all of my objects, and whenever I click, for example, Starship, it opens all of the properties of this object or all of the data providers of this object. So here I'm interested in varying the launch azimuth, the launch burnout azimuth, and downrange distance. So I'm going to select these two here by going to the propagator folder, opening the launch sequence, and finding these properties that I can modify here and select as inputs and drag and drop them here on the analyzer variables. And then I will select my delta V as outputs, the delta V related to the maneuvers that I'm doing to raise apogee and to do the plane change to equatorial plane. So I'm opening my target sequences, I'm opening my maneuver, and I'm opening my results folder. I'm selecting delta V here and drag and drop here. And I do exactly the same for the combined change, so I can see the impact that my inputs here, the azimuth and downrange distance of my burnout at launch, have on the delta V required to do my target sequences. And I'm going to also select the accesses that I compute, so make sure to compute these accesses beforehand. Open the access folder here and go to the first one, select in the data provider variables the access data folder, then the duration, and select minimum. So we will make sure that the minimum duration is equal to 0 here. To put it in another way, basically we have no access with this airspace, hopefully. And we do this for all of these accesses. So now we have selected our inputs and our outputs variables. And basically we're going to study thanks to the various tools you have here on the top bar, how these inputs that we will vary with certain lower and upper bounds and step size will impact on the outputs. Here we want to understand what are the best azimuth and downrange distance values for having minimal access to the airspace, as well as minimal consumption of delta V. Now that I have set up my inputs and outputs, I'm going to be able to do my first trade study. I'm going to use here in this case the parametric study, which is represented by this icon. So I just clicked here, and after clicking here, I have this window that's opening. So what I did already here is just drag and dropping a design variable, which is my azimuth here. So I just did this here. And then I've input my lower and upper bounds, as well as the number of samples. The number of samples is proportional to the step size. And I have my different outputs here that are set up on the right, my responses. So I just clicked on them and selected control, so I could add all of them at the same time like this. And basically this parametric study only used one parameter, one design variable that varies the way you want it. So from a lower to upper bound with a certain step size, but you can have several responses. In this case, I chose the minimum duration of my axis to see the impact of the azimuth on it. And I didn't have any idea what kind of azimuth I should begin with. So I just input a large range and a large amount of samples. And what happened is that once I ran the parametric study by clicking on the run button here, STK began to run each scenario for one different value of azimuth. So it began to just loading new scenarios on my 3D windows with a different azimuth here. And once it's finished, it outputs something called a table data explorer trade study. So the data explorer basically shows all of the results in the form of tables with the different scenarios. So in green, you can see the variable, the design variable that changes over time. And here you can see your different values for your outputs. So you can already see from the table that the best range here, so probably the range that's between Cuba and Florida, is from 92 degrees azimuth to 97 degrees azimuth, because the durations in all axes are equal to 0. And we can add a new view here to show you the plot tool that we have with Analyzer. So we're going to select the 2D line plot here, and we're going to customize it a little bit. So for now, we just have on the x-axis the burnout launch azimuth, and on the y-axis the minimum duration for only one of the axes, not all of them combined. So I'm going to go to dimensions. I'm going to click the plus and add several series, so several curves basically. In the x, I will always keep the azimuth, and in the y, I'm going to select the second min. And I'm going to do the same one for the third min. And here I can see that I have all of my curves of durations of axes, minimum durations. And I can see clearly that from 92 degrees here to 97 degrees azimuth, I have no access for any of my regions. I'm going to go back to my STK Analyzer window, and I'm going to check if my variable inputs and outputs are correct. And so first of all, I'm checking if these azimuth and downrange distance are still here. And then I'm going to add the delta V as variables outputs in order to see the change of delta V depending on my change of azimuth and downrange distance. So in order to do that, I make sure that my starship here is selected. I go to propagator, I go to my target sequences, both of them. I go to my maneuvers. I go to the results and I select the delta V and I drag and drop it to the outputs. And I do exactly the same manipulation for the combined change target sequence here in order to have set the delta V as an output. Then I click on the carpet plot tool here, represented by this icon, and I will be opening a window that looks like this one. And then in my design variables here, this time I can input 2 design variables instead of 1 compared to the parametric study. So that's the interest of the carpet plot. Keep in mind that when you are using 2 variables, it means you are making n times more runs. So that means that whenever you're doing 10 steps here on your first variable and 10 steps on your second variables, it means you're going to do 100 runs in STK. So here I chose the burnout, launch, azimuth, and burnout, launch, downrange distance as my 2 design variables that are varying from 92 to 97 for the azimuth, because I managed to see that this was the best lower and upper bounds for my accesses where I didn't have any access with my airspaces. And then I selected a random lower and upper bound for my downrange distance because I'm not entirely sure what impact it has on the delta V yet. And I know that it has no impact whatsoever on my access duration as well. So I selected 3,000 to 5,000 kilometers. And in my responses, I selected both of my delta Vs. And then I run this carpet plot tool. And I run it, and it ran STK for 100 types of scenarios with different values for these design variables. And I have saved this result here. So I have my data explorer with a finished results. I'm going to do what we call a contour plot because I have 2 design variables and a Z axis. So I'm going to click on Add View, Contour Plot. And here I'm going to see that as my azimuth decreases and my burnout launch downrange distance increases, my delta V decreases. Of course, not by much here because we are extremely constrained when it comes to azimuth, but it makes physical sense. Why? Because we're doing prograde burn to reach a higher apoapsis, and then we're going to do a plane change maneuver. So that means changing our inclination. And if we start with a higher inclination, which means if we start with a higher azimuth here in this case, then it's going to cost us more in delta V to get back to the equatorial plane. Now I learned 2 things from my 2 different studies. I learned that the azimuth of my burnout launch is the most important parameters when it comes to buff access and delta V reduction. And I also learned that the burn launch downrange distance that's the most optimum is probably between 3,800 kilometers and 5,000 kilometers, although this is not the most important parameter. So what I can do now is narrow down my lower and upper bounds of my different design variables in order to set up what we call optimizer. So now let's use optimizer to find the optimum azimuth for our situation here. So we're going to click this icon here, optimization tool, and in this window here, we're going to design a few different variables. So my objective here is to minimize both delta V's here. So whenever I drag and drop these parameters, it's already set to the goal of minimizing, but I could have set maximizing or solve for depending on if I add other goals. But here I want to minimize my delta V. As a constraint, I want to make sure that my access duration are always equal to 0. So I'm going to modify the lower bounds to be 0 on all of them. And finally, on my design variable, I'm going to choose the azimuth here and the burnout launch as my design variables. I'm going to start with a starting value of 2 because we saw that's where we started to have no access, and with 3,000 kilometers for my starting value for my downrange distance until 5,000. And here 92 to 97 because we already know, thanks to parametric study tool, that this is the best range to have no access so far. And here I have a little choose button on my algorithm that helps me to choose what algorithm is the best adapted to my situation. So it's kind of a wizard. I can answer these various questions. So yes, my objective and constraint functions are smooth and continuous. I do not really know how quickly my model runs, so I'm just going to assume the worst scenario. Same here, I do not know if the model has failed run so far, and probably the design explorer is the best solution here. So it's choosing it as my solution. I'm going to run this. My optimization algorithm run in 1 to 2 minutes here in this situation, and it's exported a data explorer table just as before with the other tools. But what I'm really interested in is seeing the output. So I'm going to go back to my optimization tool window that I used just before. I'm going to click on the view output button on the right bottom here. And so I can go to the best design tab here, and I can immediately see the best results for my design variables, depending on how to minimize the most of the total accumulated delta V between my two maneuvers here. Keep in mind that the delta V here is set as kilometers per sequence and not meters per sequence. So I can finally find that my optimization algorithm found that the best value for my azimuth is 92.3125 degrees, and for my downrange distance, 5,000 kilometers. If I go back to my optimization tool window, I can see that there is a button called Sync to STK. So whatever values that are last updated as the best values here in this situation, I'm going to simply sync them with STK with this button. And so it will copy these properties to my STK scenario. And if I go back to my Astrogator satellite, I will see that that's what input here. If I check my burnout, yes, this is the best values from my optimization run. Now I'm going to go back to my STK Analyzer window, and I'm going to use a tool that I think is extremely interesting in the case of launches. This tool is called the probabilistic analysis tool. So it's represented by this icon here. And I'm going to be able to input errors basically based on different types of distribution on my design variables. So I'm going to choose my two design variables. Here I drag and drop my launch azimuth. So here I'm just going to keep it simple and keep a normal distribution with a standard deviation will be the only parameter that I'll change, and this parameter will be equal to 0.001%. And I'm going to do exactly the same thing for my burnout, launch, downrange altitude, with a mean that's starting as the best solution that I found earlier with Optimizer. So I'm going to do the same standard deviation here. Okay. And then on the outputs, I'm selecting my delta V's, my minimum access durations, and I drag and drop them here. On the number of runs for computation purposes, I'm going to only select 100 runs. It's going to take a while, so I will show you the results immediately here. Once the run is complete, I have a nice histogram plot that shows me the repetition of my different scenarios here with a median of 92.31, 254 degrees for the azimuth. In our case here, I can have the same. So this is the histogram related to the azimuth, but I can also change it to the downrange distance by clicking dimensions and changing the x here. So I can see how my samples are generated here randomly and all of my statistics. I can also open a nice new view, which is called the scatter matrix by clicking the Add View button. And this scatter matrix is basically taking all of my parameters and comparing them to each other in a matrix. So parameters on the right are not correlated at all because it's the axes versus the delta v's, so they're not related to each other. So obviously we won't see any trend here. However, we can see, for example, the trends of the burnout azimuth with the amount of access time. In this case, we set up a burnout azimuth that is optimized right for the minimum access duration. So it's going to stay to 0 even if we have this kind of standard deviation error. So we're pretty safe. And when it comes to delta V, we also don't have significant changes despite errors in the azimuth. And we have the same conclusion with the change in downrange distance of our burnout. At the end of our scenario, we managed to use many tools that Analyzer has to offer. We managed to show that Analyzer can be used both with Access and Astrogator in order to define new constraints that we usually are not able to define within Astrogator alone. These constraints here were the minimum access durations with our airspaces that we don't want to violate with our launch. We also managed to define, thanks to the parametric study and the carpet plot, which input variables are the most detrimental to our study. And we managed to see that the azimuth at burnout is the most detrimental one. First of all, because it defines your launch angle here, initial launch angle. So it defines how you can avoid having access with your airspaces, first of all. And it also has a huge impact on your delta V compared to the downrange distance, for example, because this azimuth at burnout determines also your initial orbit inclination. And if you have a higher inclination at your initial orbit and you're actually trying to get into an equatorial orbit with an inclination equal to 0, then you're going to burn more fuel. So we managed to show these two things, and thanks to these parametric and carpet plot studies, we managed to also see which were the lower and upper bounds for our design variables, both the downrange distance and the azimuth at burnout. So we managed to see which are the optimum bounds for these two design variables that allowed us to set up an optimizer tool run that was more efficient to start from because we had more defined bounds. And we managed to show that Analyzer can allow us to find an optimum value for our design variable. In this case, the downrange distance was 5,000 kilometers, and our azimuth was 92.3125 degrees. And lastly, we saw that we were able to input errors into our runs and define the standard deviation for these errors or the type of distribution. And this is a really important part of launch safety.